Hello, class. I see that my microphone is on and on my head at the same time, which both of those two work out best for the audio of the lecture. So what I wanted to do with this lecture is I'm looking at polar moments of inertia for, really, when you think about it, what would we look at polar moments of inertia for? Wouldn't that be for like a torsion rod? Let's say that I had a torsion rod like this, right? That was, I don't know, in your car or something like that, the crankshaft in your car, the drive shaft in your car, something like that. So I've got a torsion rod, and we'll say that that there's a torque, right? A torque on that torsion rod. Now, if before I actually torqued on that torsion rod, I had drawn a line down the side of it, right? What would that line look like after I started torquing on it? It would, this part, because this part is embedded in concrete, sorry, that's what, whatever, let's just say that it's embedded in concrete, right? So it's not going anywhere. But what would happen to this end of it? It would go down, right, along the length. And so there would be a twist. And in fact, if originally I drew a line from the center here out to here, after it had been twisted, wouldn't the line be more down here, right, as this would twist? And in fact, we could say that this would be an angle of twist that the torsion rod had twisted. In fact, we call that angle theta. Now, there's an equation for theta, which we're going to get to when we get into solid mechanics, strength of materials, and it's TL over JG. And I've told you before that the maximum stress, and I'm not sure if it's a capital gamma or a tau, but that maximum stress is equal to TR over J. Now this would be the outermost radius. A torsion rod always breaks on the outside and then the crack travels inward, right? I just want to point that out to you if you're ever in that situation. Can't think of when that would crop up, but who knows? And so you can see in both of these two equations for torsion rod, we have the polar moment of inertia. So that's what I wanted to talk about first, is the polar moment of inertia. And really, what the polar moment of inertia is J equals the integral r squared dA, right? Now, what is r squared? Isn't r squared just the x squared plus y squared, right, dA? Can't I break that up and say that that's the integral of x squared dA plus the integral of y squared dA, right? I think everybody can see that this is just going to be I sub x, and this is going to be I sub y, right? So there you go. J is equal to I sub x plus I sub y. And where J really comes into play is here, where we're looking at a circular cross section, because who would make a torsion rod out of anything except for really a circular cross section? I mean, how many? Anyway, don't worry about it. Circle is the thing. So, what is, if we look at the well, we could just look, as you can see on our sheet here, which is right out of the book. This is out of the back leaf of the book. So I'm sure that you have it. you can see what the moment of inertia of this is. I of x and I of y are both pi r to the fourth over 4. So pi r to the fourth over 4 plus pi r to the fourth over 4. And of course, they're both the same because it's symmetrical, isn't it? Right? Whether I'm going with the x or the y-axis, it's going to be symmetrical about that. It's axis symmetrical. So of course, those have exactly the same. Now what we're looking at, though, is the polar moment of inertia. The moment of inertia about the z-axis, you might say. And that's going to be pi r to the fourth over 2. And of course, that comes in very handy because look at what we're doing over here. We're using J there. We're using J here for torsion rods when we get up to, torsion in strength of materials. So we're going to want to know how to calculate J for any type of cross section. And that's what I wanted to do with the polar moment of inertia, right off the bat in this lecture. Now, after that, though, I wanted to go into deriving the moment of inertia for a triangle, like I said I was going to do earlier. So let's put that triangle up there just a second. And then we're also going to use the transfer formula or parallel axis theorem. I think transfer formula is used more for mass moments of inertia, maybe. Parallel axis theorem is used more for area moments of inertia, but anyway, I look at them as interchangeable because they pretty much say exactly the same thing for the two different moments of inertia. Now, what I want to do is I want to use the same framework that we used when we were figuring out the centroids for a triangle, right? So I'm gonna use this as my origin for my x and my y axes, and then I'm going to just make a right triangle. I don't have to make a right triangle, but it's just easier to do the integration and stuff, so it can be any triangle. Don't worry about it. All right, so now what I want to do is I want to find it about the x-axis, right? So about the base. And so if I find it about the base axis of that triangle, what is my moment of inertia? Let's go back to the definition of moment of inertia, right? It's y squared dA. Right? And so we have to really find out what the, here, let me draw a dy. Let's just, let's say this is going to be my dy. Now, what does this go? This goes from 0 all the way up to, I better label that actually. This is A. That would be A, and then this would be B, right? Okay, does everybody see that? A and B for my X and my Y for the triangle. Okay, so when I'm looking at this very small thing here, first I'm gonna still do the integral from 0 to B, right? Because we're going up, in the Y direction. We're summing all of these together from 0 to B. And it's going to be y squared. And then we know it's going to be dy. Let me just put this in here. So we know that we're first going to have dy, but what is dy going to be multiplied by? And if you remember the last time we did this, we used exactly the same layout, and I'm going to refer you back to that earlier lecture. I used this, I don't want to go through the whole thing again because I did it exactly the same so I didn't have to. It's A minus A over B times Y. So I probably should have put brackets there, but I don't know. So I'll put brackets here for sure. But So you can see that as we work through this, we're going to have two different things, because dy is going to be multiplied by both of those. So what I want to do is I want to break this in half. I'm going to have to write it down here. So this is about the base. And I'm going to break this in half into two integrals, 0 to b. They're both going to be from 0 to b, of course. And then the first one is going to be a times dy, and of course y squared. So a y squared dy, because dy transfers through both of those, right? All right. And then the second one, because you see the minus, and then let's, of course, we have the same extents for this integral from 0 to b. And we're going to have a over b, and then y times y squared times dy. So y times y squared is y cubed. So a over b times y cubed dy. All right. Now let's solve those. The first one that I've got, a y squared dy. Well, y squared is going to become y cubed over 3, right? And the only thing I'm throwing in there is b. So it's going to be a b cubed over 3. I think everybody can see that. A b cubed over 3. The second one that I've got here, so minus, I've got a over b, and then y cubed, which is going to be y to the 4th over 4. And since it's b, it's going to be b to the 4th over 4, right? A over b times b to the 4th over 4. Does everyone see that? Does anyone have any questions with how I got either one of those? I left it this way without canceling it out, which would be another step. And I think I will put that step in there now because you can see that that b is going to cancel out with one of those and make it b cubed. So I've got ab cubed over 4 and ab cubed over 3. Now, really, this is 4 ab cubed over 12, isn't it? Did I turn that on? I did. Well, that's good. Minus, and then that's ab cubed over 4, so that's really 3ab cubed over 12, too, isn't it? So what we get out of that is just ab cubed over 12. Now that is not around, oh, that's a cubed, remember, ab cubed over 12. I'll write it out again, ab cubed over 12. Now, what I want you to remember is this is the thing around the base, right? That is Ix base, not the centroid. So that's what I want to do. What is I sub CC, right? What is the thing about the centroid? What should I use to draw the centroid? What color? I've got some new colors here. I just don't, I don't know. There you go. Well, how about that one? So where is the centroid? It'd be about 1/3. Let's see, that's 1, 2, 3. So I'm going with the centroid is pretty much right down the middle of that. I drew the centroid, it just must have been instinctive. So that's about the centroid going up there 1/3 of the way up. All right. So this is going to be then, if that's b, it'd be b over 3, wouldn't it? So it would be what this is, Ix of the base minus the cross-sectional area of the triangle, right, times the distance between those two squared. All right. So I've got AB cubed over 12 minus, does everyone see why it's minus? Because the centroidal, the moment of inertia around the centroidal axis is always the minimum. Always the minimum. I sub CC is always the minimum. Right? Always the minimum. So we've got to subtract this off there. And what I've got is the cross section of this. So this is just going to be A times B over 2 times the distance between there, which is just B over 3 squared. Right? So what I get is I get AB cubed over 12 minus AB cubed over 6. Have I done something? Wait a second. I'm going to take a break for a second. Obviously, I've made a little mistake here. Well, thank God it didn't take me that long to realize what I had. I was like, what? Yes, of course. And I don't have anything. Oh, I do. I do have a new mark out pen that is supposedly even better than the old stuff that I was using. Look at that. It marked it out immediately. Maybe not as good as the other stuff, but of course, squared refers to the 3 as well as it refers to the B. So that's 9. 2 times 9 is 18. I'll just put it there over a little bit over to the side where that dries. And so if I look at this, I could do it all in 36s, couldn't I? So this would be 3AB cubed to the over 36 minus 2AB cubed over 36, which leaves me with AB cubed, that's a cubed, over 36. And of course, that is a lot smaller than AB cubed over 12, isn't it? It's 1/3 smaller. And of course, that is the difference between the centroidal. I just like putting lines over everything that's a centroid. Moment of inertia and the moment of inertia around all of the other things. All right, now we've gotten through the polar moment of inertia. We've gotten through the triangle, figuring out the triangle, and transferring it down to a new location. So I have some extra time here, and I have some extra whiteboard. I'm going to just call it a whiteboard. That's my whiteboard. Although I can't erase anything, because now my eraser really has gone downhill. Let me have a sip. And so what I want to do next, instead of going through moments of inertia, we've now moved moments of inertia. We know how to do that. We know what polar moments of inertia are as compared to regular moments of inertia. What I want to get into now is shear force and bending moment diagrams. Shear force and bending moment diagrams. We're still going to get into mass moments of inertia, but it's going to be after. And the reason for that is everything that we've really done up to here, getting into centroids, polar moments of inertia, area moments of inertia, second area moments of inertia, or moments of inertia of plane, areas, or whatever you want to call it. It is all directed toward an application in strength of materials called flexure. Let's write that up there, flexure analysis, right? I'll just put anal. You know what it refers to. Well, I can't fit anything else in there. Why? Well, that's even worse. Anyway, back to shear force and bending moment diagrams. Now, when I have a shear force a diagram, or really a loading diagram, let's say that I just had a simple beam, right? I've got a simple beam. I'm just going to put a couple forces on that beam. In fact, the beam is so simple, it's just simply supported at both ends of the beam, right? How big does that mean? 1, 2, 3, 4, 5, 6, 7, 8, 9 meters long. Had to be 9 meters, didn't it? So it's a 9 meter long beam. And it's going to have, it's supported. It's a clear length across there. It's an I-beam of some kind. I'm not going to go into drawing the cross section right now because I'm just looking at the shear force and bending moment diagrams of this. So let's say that I were to, just put a force, oh, let's say right in the middle. What is that, 9? So it'd be 4.5. Right there is a force. I'll call that force P. And now I've got two reactive forces here, don't I? Right? If we sum the forces in the y direction equal to 0 newtons, we see that I've got a reactive force here. I'll call it R sub A at point A and R sub B at point B, right? Does everyone see that? So, if we sum up these forces, I think everybody can see that I've got minus P plus R sub A plus R sub B. And so that's going to give us P equals R sub A plus R sub B, right? Understand what I mean? Now, what I want to do is I want to understand what are the internal forces. What is the internal forces that are going on inside that beam? What is the maximum bending moment? I think everybody can see that really, I'm just going to exaggerate this a little bit, but if I, push down on this beam, let's say it's a 2x12 or whatever, that's 9 meters long. That's like 27 foot long. Well, that'd be the biggest tree. So, but I think everybody can see that what would happen is that we would, I'm going to exaggerate this, of course, we would start to have a deflection. And that deflection would be greatest right in the middle where the, force is being placed. Whether it's a very small deflection for, let's say, an iron I-beam that is 12 inches, got a 12-inch web, center web, or if it's a large deflection because it's somebody that somehow found a 9 meter long 2x4. It would crack. That'd be cracking. Depending upon what type of force we were putting on that, but even its own weight. Let's say 2x12. Maybe it wouldn't. Anyway, back to this. So there's going to be, some sagging and everything in the middle. And what we want to do before we ever find out what that sagging is, which is the full deflection, and we actually aren't going to get to that point in this course, but we are going to see what the shear force and bending moment diagrams are so that we can calculate what the shear stress in the center of the web and the normal forces on the outer surfaces of the I-beam, the top and the bottom of the I-beam, are going to be. And that's the, end point for learning statics and dynamics and then getting into strength of materials. All right? So shear force, bending moment diagrams. So that's what we're looking at right here. And in fact, that might be, really we'll get into that later. Let me see. Oh no, I'm going to actually put that here. Shear force / bending moment. I don't know how I'm going to get moment in there. Diagrams. Yep. So we have done those two, or at least we're introducing them here. So if I see that, I've got this equation right here, and I think everybody can also see that it's going to be, you know, symmetric about here as far as my bending moment, you know, goes too. But how do I figure out what the bending moment is? Now let's say that I have this force right here. I am going to break. It should probably be introduction to shear force and bending moment diagrams. But I am just going to break the beam mentally, not physically. But I'm just going to break the beam there so that now I have the beam and it looks like this. And I'm going to still put my forces that I have on the beam, the two different sides of the beam, right? But in this area right here, on the right-hand side, in fact, let's blow this area up. Let's take this area right here. In fact, what I'll do is I'll draw it in very small, and then I'll blow it up and I'll put it over here in just a second. I'm just going to draw it here so that, you know, so you can sort of see this. But then, you know, it's so small. Like I said, I'll have to blow that up. Let's put that over here. I'll circle it in a second. But at the juncture of where I mentally broke this up, what I've done is I've drawn some equal and opposite forces. So they cancel each other out. It's like multiplying by 1, right? So I've got a shear force that comes down this way, and I've got a shear force that comes down this way. Those are shear forces, and I'm going to refer to those as V, because usually we refer to shear forces as V. All right. Now, these other lines that I put on there, this one is my bending moment, and I'll refer to that as M. And of course, since I put one on that's going clockwise on this side, wait a second. What? Yeah. Well, where's that thing? I didn't mean to do that, and actually this works out pretty well because I was meaning to draw the thing at the other end anyway, and so the waiting for it to dry isn't even a question. So there you go. Thank God I drew it over here. So this is counterclockwise, right? And so that offsets the clockwise. So this is also M. So V, because these are equal and opposite. M, these are equal and opposite. And so what I can do is I can sum the moments and I can sum the forces on either end of this to solve for V or to solve for M, right? So at this point, if I was doing a shear force diagram, let's just drop this down for a shear force diagram, right? I'm just going to put this right across here. This is just my line, the 0 line for shear force. So let's just look at that right here. You know, we've got this. Let's sum the forces in the y direction on this end. So what we have, and in fact, we know what these are. Let's put some numbers to this. Let's say that's 100 newtons, and that would make that 50 newtons, and it would make this 50 newtons, right? Everybody sees that because it's symmetric about the. It's right in the middle. The force is right in the middle, so it's going to be equally distributed between the two supports. All right, so we know what the different things are there. So when we're looking at, and this is not V0, by the way, it's not voltage, that's just a zero, the V just happened to be there. I should have probably put it on the other side. Let's put it there, and then, oh, handy dandy. I'm getting there. Yep, I'm not talking about voltage at all. So when we then sum these on this side, I get summing the forces on the right-hand side, right? It's going to be R sub B minus P plus V equals 0. Does everyone see why it's plus V? That's right, isn't it? It's plus because V is going up. So what this tells me when I put these actually in here, because this is 50, this is 100, and then I've got V. So 50 minus 100 is minus 50. Throw that on the other side, and so it's 50. So I know that this implies that V equals 50 newtons. Sorry, 50 newtons. So at this point, it equals 50 newtons. Let's just drop that down there. Doot, 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 doot. So I know that at that point it equals 50 newtons. How about if I was to move this here? Does it change? No, it's still 50 newtons right there. How about if I move it over here? No, it's still 50 newtons. Nothing's going to change until I get to P, right? So until I get to where the force P is being placed, all of this from the point over here all the way over to there is going to be 50 newtons, right? Now, once it gets there and I break it here, let's do an analysis on the right-hand side again. Well, now, okay, so this is at, let's call this point, oh boy, what's a good, point T. So at point T on the right-hand side, it's that. Now let's do it again on the right-hand side, but at point, I don't know, we'll call it U, right here. Point U. Now all of a sudden we've got R sub B plus V. R sub B plus V, right? V doesn't change. It's still broken up that way. We're still on the right-hand side of the beam, right? So that would mean, and that equals 0, that would mean that V there equals minus, because this is 50, minus 50 newtons. And in fact, it doesn't change from there all the way over to the end, does it? So my shear force diagram looks like this. And in fact, I'm going to color it in a little bit. We'll use our orange here like we did up above it. And so you can see that that's my shear force diagram. And V, of course, stands for shear force. Could I have done it on the other end, done the analysis on the other end, and gotten the same thing? I don't know. Let's see. Now, if I did it on the left-hand side, let's sum it on the left-hand side at point T, right? At point T right here. The left-hand side would have R sub A, positive R sub A, but then minus V. See how V on the left-hand side is always negative? And that would equal 0. So what that tells us is that V equals R sub A, which is 50. So V equals 50 newtons. Oh my God, that is exactly the same thing that we got when we did it on the right-hand analysis, right? What do you think that if we were to do it at U on the left-hand analysis, we'd get the same thing too? So, you know, that's right. And of course we would. I'm not even going to do it because this is how we're starting now. We're putting this and understanding shear force diagrams certainly is going to teach you a lot about structural engineering, and it's going to, you know, bring your mind, actually get you involved not only in the mechanical engineering side and structural engineering mechanical, but also understanding a lot of civil and being able to talk intelligently with civil engineers as well as mechanical engineers. All right, that's it for the lecture today, and I don't know if I'm making any more lectures today, but I'll see you at the lecture tomorrow. Let's say that. See you there. Bye.